So I will start. Good morning, good afternoon to everybody all over the world, and welcome to our ESO Exoplanets Atmospheres workshop. So it's obviously, as the name suggests, this workshop is really specific, and it's specifically on detection, characterization, modeling of exoplanet atmospheres. As you all have seen, obviously, the workshop technically already started on Monday, and the last 2 days we've had hands-on session where we had a selection of around 35 or so students and young postdocs joining us for a number of hands-on lectures where different lecturers went through different aspects of data processing, data analysis, and modeling of exoplanet atmospheres. Again, as I said in the email, I do apologize that we weren't able to accommodate everybody who wanted to join those sessions, but this was done on purpose to make sure that we could actually kind of answer questions from the students and kind of have a bit more kind of intense discussions. And we thought that if we have too many, then it will be difficult to kind of follow a train of thought. But nevertheless, we recorded all the sessions and we have put all the materials needed to follow those lectures on a GitHub repository. You can find the links to the YouTube videos and the materials for all the lectures in the program already for the first day. For the second day, I promise you I will get it done hopefully today or earliest mid-afternoon tomorrow, so you will have access to everything. Please do have a look and try and follow the Google Colab or IPython notebooks that are there. And I promise you, once you do go through these lectures in the next 3 days, will make a lot more sense to you, especially obviously to those that don't specifically work in this field, but they would like to get started. Just a few quick organizational points. If you have any questions, please put them only in the chat. So during the talks, we will only be monitoring the Zoom chat. So do not put anything in the Slack during the talks. So the default setup is that you will raise your hand or put your questions in the chat, and the chair will raise them with the speaker at the end. So we will not interrupt the speakers during their talks. However, this is something for all the speakers. If you prefer to be interrupted middle of your talk and kind of have more of a discussion type, please say so at the beginning of your talk, so the chair knows to basically give you the talk in the middle of the presentation. In case you do not want your talk to be recorded for whatever reason, please let me and Eleonora know, Eleonora Lay, who's also there, so that we will stop the recording. And so that's completely up to you. So for those of you who have joined the Slack, we have a dedicated Slack channel for the conference, and we have created for every day a separate discussion thread, and those are called intuitively Tuesday, Wednesday, Thursday, Friday. Please make sure, if you want to continue discussing with whichever speaker, you put your question to the speaker, @ing that speaker, so that they know that the question is for them. And if you want to continue discussing, please make sure that you continue discussion in a thread and not in the main channel, so that so basically the discussion doesn't get lost or they don't get mixed up with discussions for other talks. I know this is not so easy to do, but please try and stick to that. For all the speakers, please send me your either PDF or whatever software that you make a presentation on the Atmo 2021 email. I will put it in the chat now, so that we can put them of course on the website. Again, if there is anything in your presentation that you do not want to be, you do not want to be included in what we put on the website, because remember, whatever we put there is public. So just delete anything that you do not want to be included, or if you do not want your presentation at all to be put online, that's also it's up to you. So just let me know, and we will not put it online. From my side, I think that's all I want to say. Oh, just one last thing, please do read and remember the ESO code of conduct for conferences, which you can find again on the conference web page. I think, yeah, without further ado, I would like to introduce to you the first speaker that we have, Julia Seidel, who is invited speaker, the first invited speaker that we have, and she is from still for now University of Geneva, but not for too much longer. And yeah, she's going to talk about narrowband transmission spectroscopy using high dispersion cross-dispersed shell spectra. Again, I encourage you to look at her brilliant lecture from Monday if something is not really clear, the method that she's using. Okay, Julia, it's all yours.
All right, well, thank you for the very nice introduction. I hope you can all hear me well. Without further ado, let's dive right into it. So just as a disclaimer, as you can already see here, these are the VLTs of ESO, and this talk will be heavily biased towards ESO high dispersion spectrographs, and it will be heavily biased to other European spectrographs, simply because that's what I work with, but I've tried my best to try and level it out a bit. But if your favorite spectrograph isn't here, please don't be too upset. All right. First things first, a little bit of an overview. I'm gonna do a little bit of a repetition from the Monday lecture that Nuria Casas-Borges and I gave, to go over the theory, go over the caveats that apply when you do this actually in reality. Then I'm giving the tiniest of introduction to a few of the spectrographs that we use and what we've done so far with them as a field. I'll talk about the resolved lines that we've detected so far and what we can do with them, and where I think we might go with this, or where I hope we will go with this. So for those of you that followed the lectures, this will be a repetition. For those of you that are very ingrained in the field, this will be nothing new, but I've kind of aimed this, this overview talk at master and early PhD students so that everybody has the same level of knowledge once we dive into the talks in today's session. So what happens during transit and what we need to do transmission spectroscopy is we wait that the stars align quite literally, so that between us and the star that we observe, one of the planets just happens to go in front of, so that we can see when we observe the star this dip in the flux that we have, simply because the planetary disk is in front of the stellar disk, and this will be proportional to the size of the stellar disk to the planetary disk, so we can learn something about the size of the planet. And if we now look at this a little bit more in detail, if you imagine on the left of you, you have the host star, and then we as the observer would be on the right, and we have this rather bloated and not to scale exoplanet in front of it. And you can see here an atmosphere mostly made out of the white hydrogen and helium atoms. And then you also have some other trace metals in there, and I picked sodium just to like emphasize the point here. And yeah, okay. When now the light comes from the host star to the observer, part of it will be blocked by the exoplanet, but a very tiny fraction will actually go through the atmosphere before it comes to us. So a little bit will be scattered, and a little bit will actually be absorbed by the elements that are in the exoplanet atmosphere. And depending at which wavelength these elements absorb, you'll see a different wavelength that the light doesn't come through to us through the atmosphere. So the planet will look very big if the element that absorbs is in all of the atmosphere, or a little bit smaller if the element is not in the entire atmosphere. And the reason why I picked sodium here for the depiction is because sodium has a resonant doublet in the yellow optical wavelength band, which has been used already for historical times, basically to look at spectral lines, but also in Charbonneau et al. In 2002, with the HST, so not in high resolution, they use these resonance spectral lines where you need only a very small amount of sodium to actually see this absorption to detect an atmosphere for the first time. Now, fast forward a few years, about a decade, we have the HARPS spectrograph that was designed to find planets, but is also very good at characterizing planets because it can actually resolve this absorption feature this finely in wavelength that we can really see the two lines and not just the binary absorption or not absorption. What you can see here very clearly is that the relative flux, so this dip of light that we get is proportional to the height in the atmosphere. So whether I talk about absorption depth or about height in the exoplanet atmosphere is equivalent. All right, so let's dive right into it. Once we did all of this, we get this wonderful spectrum. This is what a sodium doublet from real data looks like. This is for the hot Jupiter HD 189733b, and is taken from Wittenbach et al., published in 2015, where they used 3 nights of HARPS data and got this very beautiful doublet out of it, nicely resolved. And that you can already see that they went a little bit further than just detecting the sodium and being able to say that it goes up to 1.2 planetary radii, but they built kind of a Frankenstein model where they just sliced this data into horizontal pieces and then fitted a theoretical transmission spectrum to it to kind of get a temperature profile that in the lower atmosphere, it's cooler than in the higher atmosphere, kind of pointing towards a temperature inversion, which led them to believe that the sodium actually reaches up in the thermosphere and probes the first parts of the temperature inversion. So that was a very cool first work. But to get there, you have to do a little bit more than just point the spectrograph towards a planet and hope for the best, because this theory clashes with reality very fast. So if you followed Nuria's lecture, and if you followed all the lectures on Monday, also Eliar's lecture on molecule, you know that there's a lot that can happen between observing and actually getting resolved lines. First, we have the planetary and the stellar signal that both sit on top of each other. So the planetary signal will move on top of the stellar spectral lines. You have to be very careful with your signal to noise ratio, with your overall flux, and how the lines sit with each other, and also correct for these velocities. Then also we have telluric lines for us in the optical and in the near infrared. Water and oxygen are the most important ones that we have to correct for, which we do with molecule. So I encourage you to look up the lecture from Monday on that. And just to show you how important it is, this is a plot from Esparza-Borges et al. In 2019 on Mascara 2b, a hot Jupiter. And all of these kind of red tinted lines, all of that is tellurics. So this is, I think, the most heavily tellurically contaminated spectrum I've ever seen. When I looked at her paper, I really felt for her because I know how hard it is to correct for this. Another thing that we have to take into account is telluric sodium emissions, because we have sodium in our own atmosphere. Isn't that great? Which means that either just because of the yearly cycle that these emissions go through, or because of meteor showers, the sodium can get excited and then emits. So if we want to look for sodium lines in particular, this is something we need to take care of and look at it. So this is what happened, for example, here. This is for a sub-Saturn, WASP 127b, where you see 2 nights of observations, the stellar spectra taken with the HARPS spectrograph. And in one, you see here this inset that's kind of the line, the point of the sodium line here, because in this particular planet, the telluric sodium emission and the stellar sodium lines really lined up, unfortunately, very beautifully. So you have one night where you have the really nice form of the line, and then we have another night where you can really see the sodium emission rather staggeringly contaminating everything. And this can lead you to think there's a gigantic sodium feature, when in reality, it's not there. All right, I haven't even started talking about any form of stellar contamination, granulation, the Rossiter-McLaughlin effect, gravity darkening, all of these things. If you want to do narrowband transmission spectroscopy, look at the papers by Heather Stegler and also by Nuria Casasayas-Baris, who are the ones who know really what they're doing there. But this is not my specialty, so I normally leave that to the experts. Now, if we move to the spectrographs, the disclaimer is, I didn't take all of the spectrographs into account here. There's a lot of mid-resolution spectrographs, like here at the Hubble Eberly telescope, that I will not talk about. They do fantastic work. So if you ask yourself, oh, could I do narrowband transmission spectroscopy with this spectrograph? It's not 100,000 in resolution, or it's not super stabilized. Just go for it, and then you'll see. So don't be constrained to the list of spectrographs that I'll show right now. So starting off with the working horse of ESO, which is the Hubble spectrograph at the 3.6 meter telescope in La Silla, where I just showed you before this really nice spectrum that I think was one of the first spectra where they moved from planetary detection to atmospheric characterization in Wittenbach et al. Where they found this really beautiful sodium doublet that reaches up until 1.2 planetary radii, so it's a very large feature. But we're obviously not constrained to sodium and narrowband transmission spectroscopy, but we can also look for other resolved lines. For example, this is together with Speck et al. 2018 in low resolution. It's the first high resolution detection of the helium triplet in Ayar et al. 2019, where they used the Carmenes spectrograph at the 3.6 Calle Alto telescope on the Canary Islands. This is really pretty. I mean, you can first of all see two of the triplet lines are really merged together. So this is why it looks like a doublet. And it really gives you this beautiful line shape that reaches all the way up to around 7%, so 2.2 planetary radii, which is of course due to the fact that helium is one of the main constituents of these gaseous atmospheres. So you see very, very big features. And one of the very important things in all of physics, but also for astronomers, is can I reproduce what I see, especially if you have first results or if you have kind of unbelievable results in quotation marks. So this is a really strong detection with Carmenes, but it was very important that about a year later, Kirk et al. Used the near-spec spectrograph. So this is all happening in the near infrared at the Keck telescopes in Hawaii to reobserve the same target. And they found not only that Carmenes did a good job and that the shape that Carmenes observed is correct, but they were also able to drastically increase the precision. So if you just remember the size of the error bars here, and then you look at this, like this is a 30 sigma detection. So absolutely ludicrous result. I loved it when I saw it for the first time. So this really shows you what you can do and how important it is to reobserve targets with a different spectrograph. Now, you can obviously not only reobserve the same target with a different spectrograph, but you can also combine different spectrographs. So here's a very interesting result from Chen et al. From last year, where they observed a hot Jupiter with two spectrographs, HARPS, that I just introduced before, which sits at a 3.6 meter telescope. And then it's, well, not really sibling, but more twin in the Northern Hemisphere, which is HARPS North. That functions quite similarly and also sits at a 3.6 meter telescope. And they used the data from these two to combine them and then not only find the sodium doublet, but also the first line of the hydrogen Balmer series that you can see here on the right. So another really nice detection and a line that is even deeper than the sodium doublet, so you can probe even higher altitudes with the Balmer line series. So that's very interesting, and keep that in mind for the next part of the talk. Now, just to illustrate that you don't have to have the same spectrograph to combine spectra. So HARPS and HARPS North are twins, but you can also use spectrographs that are somewhat different. So here's again Carmenes on the Canary Islands together with HARPS North. And you can see that despite them having different error bars and a little bit of a different resolution, they give extremely similar results. This is again for Mascara 2b, and despite the heavy telluric contamination, NURI was able to really beautifully resolve the H alpha lines here. All right, So let's dive a little bit deeper. So we've talked a lot about spectrographs that sit at around 3-4 meter class telescopes, and you need a few transits to get good results. On the one hand, that's great because you know that your result is reproducible, but you can even go a little bit further than that. So this is the sodium doublet for the ultra-hot Jupiter WASP-76b from 3 nights of HARPS transits. And for those of you that did the workshop, this should look familiar because in the workshop, you actually analyzed this very data set for 1 night and were able to see the sodium doublet appear just in 1 night. So this is 3 nights combined. But what happened here is that the sodium doublet appeared to be very, very broad, much broader than what you would anticipate from theoretical predictions of what sodium and the pressure broadening for sodium should give. So this was also the first detection for an ultra-hot Jupiter where sodium should be ionized. So there was quite a lot of skepticism in 2019. But thankfully, a new spectrograph came online, Espresso at the VLT. Espresso is basically the big sibling of HARPS, and it sits at an 8 meter class telescope at the VLT. And Tabanera et al. Reobserved WASP-76b and was able in just 1 transit to see the very same, also very broad feature. So this is only 1 night, 1 transit up here, and then again, 1 transit and 1 night down here. And you can see both of them are compatible, and they're compatible with the HARPS results. So that shows you, first of all, the new spectrograph Espresso is doing correct work, and also that we didn't make any staggering mistakes when we analyzed the HARPS spectra. So that's great. Disclaimer, I absolutely love Espresso. I think it's a wonderful spectrograph, and I love how precise it is. So if I lose myself in a little bit of a fangirl moment for the next few minutes, please, I apologize. All right, let's talk about the result lines that we've detected so far and what we can do with them. So now that you kind of have an overview of what the different spectrographs do and what their spectra look like. And let's stay with Espresso, because Espresso has a superpower. It can not only be at 1 VLT that has an 8 meter mirror, but it can be fed from all 4 of the VLTs that you saw in my very first slide, and then basically get the power of a 32 meter telescope, which is rather impressive. And this is what you can see here for WASP-121. So you see the very, very precisely resolved sodium feature, and you can also see just how gigantic the hydrogen line is, and also how precise it is. But now that we have this kind of precision and this kind of photon collecting power, we can expand and look for much more lines. And this is just a section of lines, so much bigger and much smaller ones actually. And this was published in Borsa et al. This year. And I think the best plot of this paper is mostly overlooked because it's this overview, how deep the different resolved lines probe. So you can see here, there's a few new ones that can be resolved with Espresso in the 1 and also in the 4 UT mode, lithium, magnesium, potassium, and so on. And then we have the culprits that you already know, the H alpha line from the Balmer series that kind of probes up to the rush lobe, sodium that sits somewhere in the middle here, probing the thermosphere, and then some ionized lines that get dragged by the magnetic field much farther outwards than that. So this is really interesting because now we have different spectral lines that probe different altitudes. So we don't have to do the Frankensteinian approach of the Wittenbach et al. Paper anymore and use different slides of the data to fit a temperature profile, for example, where we can just use different lines that fit different altitudes and then get a much more precise prediction from the observational side of things, what temperatures we should have at different altitude levels. So I think it's very important to mention that I think one of the most important things that we can do in the next few years is fill the gaps, so to say, in this plot. So the different altitude ranges that we haven't covered yet, or that elements that might not be present in certain exoplanets, I think these can be covered soon when we get our infrared, near infrared power in the Southern Hemisphere back. So CRIRIS Plus will come online very soon at the 8 meter class VLT. And all the bands that CRIRIS cannot cover, we can kind of stitch together with the red arm of the HARPS spectrograph that will come online soon at the 3.6 meter telescope. And then there's also a few spectrographs that really haven't done a lot of resolved spectral line work yet. there is the high dispersion spectrograph at the Subaru telescope that has done a really cool job with cross-correlation detections, for example, in the Nugroho et al. Paper 2017, where they talked about WASP-33b and the TIO detection. That was very cool. But I feel like there's a lot more potential for other spectrographs to also get in the game of resolved spectral lines. So now that we've seen all of these lines and that they can probe different altitudes, so what can we actually do with them in the end? What's the game here? Because from cross-correlation techniques, we can also say whether these elements are in the atmospheres. We can say this even for elements that don't have resolved lines. So why do we want to resolve lines? Well, we want to do this, first of all, because we can provide a vertical structure. How high up are these elements? But also we can say much more than that. So for example, this is a plot from Yanadal 2019, where they looked at different calcium lines. So it's all the same species, but different lines. You can see the ionized triplet in the near infrared on the right, and then the neutral calcium on the left. And they found here for WASP-33b that there's no neutral calcium, but there's a lot of ionized calcium. So you have these different lines that probe different altitudes, and it might even be possible, once these lines are resolved better and there's less noise, to say something about the ionization rate, because you can see the neutral lines and you can also see the ionized lines, and you have also access to calcium plus that we've seen before. And one of the things that they postulated in this paper is, okay, we see these ionized lines, but they're much deeper than we expected, theoretically speaking. So they thought that there's maybe winds carrying the calcium upwards into the higher layers of the atmosphere. And I found that quite interesting. So I dove right into this and I was like, okay, let's look at winds. So I created a code that can create a theoretical transmission spectrum and fit it to the real data via a nested sampling retrieval algorithm. But then I also added a three-dimensional calculation of wind patterns in the atmosphere. And it was like, okay, let's Doppler shift by these different wind speeds in the different cells of the atmosphere and see what happens. And this is for HD 189733b. So this is the very same data set that Aurélien Wittenbach used to fit the temperature profile. And even in this paper, he already says, okay, we get this very cool temperature profile, but there's some other physics happening because we can't get the full broadening of the line. And I got the same temperature profile as him in my retrieval algorithm, which was very cool. But I also showed that in the higher atmosphere, we need like a vertically expanding wind to really explain the very broad feature of the sodium line. But because the Hubble data is still quite noisy and it doesn't have the collecting power of a bigger telescope, we can't really say much about the lower atmosphere, so kind of where the continuum and the wings of the lines are. So it didn't tell me anything about the lower atmosphere. That was a little bit of a bummer. And this is really where the power of a more precise spectrograph and also the collecting power of a bigger telescope comes into play, because this is WASP-76b, they're very similar to HD 189733b, showed a very broad sodium feature. But combining the Esparza data together with the Hubble data gives you like an exquisitely, fantastically precise data set. And with that, if you then unleash this retrieval algorithm to get some constraints on wind and on the temperature, you can actually also say something about the lower atmosphere. And what we found here is that, again, we need kind of vertical winds transporting material outwards, which is not a huge surprise for highly irradiated planet. But even in the lower atmosphere, because it's tidally locked, from a wind perspective, we have a day to night side wind that kind of streams towards the observer. I think tomorrow there's going to be a talk by Joost Wardenier that I think you should really have a look at. It doesn't deal at all with narrowband spectroscopy, but it's on the same target, and he will, from a theoretical point of view, so coming from the other end, tell us a little bit more about the degeneracies that apply to these wind patterns. And I think this is going to be a very good talk to put all of this into perspective, because what I do and what a lot of my colleagues do, we get these spectral lines and then we put constraints of what we can learn from the data in its current quality. Whereas when you come from the theoretical modeling end, you want to create a model from first principle, take all the physics into account and create the best possible model for the atmosphere and then match it to the data. But there's a lot of models that can actually fit an imprecise data set. For example, this is a very cool paper by Jens Helmecke et al. From last year, where they looked at the ultra-hot Jupiter WASP-121b. And this is with 3 HALPS nights combined. And you can see there's kind of a very curious line ratio between these 2 sodium lines. So this one appears to be a lot deeper than this one. And when you now unleash the full set of observational constraint models for the radial wind, maybe even for an optically thin torus of sodium that might even come from an external source, or for Parker winds in the very high up atmosphere, you can see that radial winds really do a very poor job at explaining the line shape, but both the optically thin torus or the Parker winds do a quite good job, as does just a Gaussian toy model. So you can see that with a very noisy data set, there's lots of different physical explanations that can be true. So it's very important to always keep in mind when you look at models to a data set that there might be degeneracies with other models if the data set isn't precise enough, and that you have to be very careful in addressing them with this, which is exactly what Jens did in this paper, to explore all of them and see where it might go. So this very same target was then reobserved with Espresso in its full UT mode. And you can just see the difference from before with HALPS 3 nights to a partial transit with Espresso. And that this difference in line depth has basically vanished. So now we have 2 super precise lines. And I hope that in a future paper, we can unleash all of the different observational models, I'll call them. So the models that we use to kind of get constraints on the physical properties of the atmosphere, where then the real theoretical models from first principles kind of have to play in the realm with. And I think this is why it's very exciting that we get bigger and bigger telescopes, because the precision mostly comes, of course, from the collection power of the telescope, but also from the precision of the instrument itself, which is why I'm personally very excited for the next class of telescopes. So there's one who's going to be built on the Canary Islands, and then there's the extremely large telescope, the ELT in Chile, with the high-res spectrograph, where we can even push towards smaller and smaller planets, because so far we've talked mostly about hot and ultra-hot Jupiters, because they're quite big, and also they're highly irradiated. So we get these resolved lines instead of the molecular bands that you learned yesterday something about in the workshop. So we'll have smaller signals, but we'll also have bigger telescopes. So we go big to go small, and then learn something about Neptunes, and at some point, hopefully, move towards an understanding of Earth-sized planets. And if you want, you can go to YouTube and Google ESO ELT, and they have an absolutely stunning 3-minute video of what the ELT will look like that I just really love. And with that, I'm going to leave you, and I hope this overview gives you a little bit of a better understanding for all of the talks that you'll listen to today.
Thank you, Julia, and also thank you for this excellent talk, and also sticking to the time, finishing early. So yeah, we have plenty of time for questions. We have like around 10-15 minutes for question discussion. So anybody would like to start? I have a hands up from Nicholas.
Hi, Julia. Great talk, by the way. I was just wondering, you were talking a lot about sodium doublet contamination. Have you ever come across contamination from the ISM?
I personally have thought a few times that I've come across it, but I have not. But I've seen a few papers where this has actually happened, which is a bummer, because you have to take care of it. But also it allows you to learn something about the ISM. So it's kind of, luck, but also unluck at the same time. But yeah, that can definitely happen. And this is also something to look out for, so that if you have a sodium feature at a velocity that you didn't really think you were going to get it, to always keep the interstellar medium in mind.
Okay, cool. Thank you.
But also, I guess if there is any contamination from ISM, it would be quite hard for it to mimic an atmospheric absorption, right? Because ISM stays in the same place during your observations, whereas the atmospheric line is moving.
Yeah, so you'll most likely, I mean, what I normally do is just when I get the data in all of the different rest frames, I just build a master spectrum and sum all of it together, and then I have a look if I see any random weird features. And normally that will tell you directly if there's something happening with the ISM or not, because it will be stationary, which is kind of cool because it's easy to take care of, but also makes it then hard to get rid of.
Files that prevent compiled model in the first.
I didn't really hear that. Was it my sound that cut out or the other one?
Did somebody want to ask a question?
Or join the discussion on ISM?
I think it was just maybe accidental unmute. Please go ahead.
More questions?
Yeah. No, is there any more questions? The plot that you showed, I think, is from Tavernero, that had a bar chart of different scale heights at which, yeah, this one.
Oh, it's from Tavernero at all.
It's from Borsa, sorry.
I think it's from Borsa at all. Otherwise, yeah. I apologize to Hugo. I'm so sorry.
No, you said the right thing. I mixed up. I mean, those effective planetary radii, to me, they seem absolutely huge for calcium. And
yeah,
so
but
the thing is,
look at the error bars, they're also very huge.
They are huge, but I mean, because obviously the signal to noise at the calcium doublet is quite low, whether from espresso or harms, right? So these are actually also indicative of magnetic activity, and these could possibly mimic your planetary signal, because obviously depending on the V-sign I of the star. Do you know if this was really considered that much? Because
I mean, so they wrote a section about how this large signal could be due to the elements being carried along the magnetic field. But if they really took care properly of the magnetic fields, I mean, this is kind of the running gag in our field, right? I mean, could it be magnetic fields? So I'm actually not sure. You should ask him.
Everett, question for me.
Hey, Julia, awesome talk. Could you go to this slide where you kind of show, I think it was Jens Hoymaker's plot of the different models over the data? Yes. Yeah. I'm just kind of wondering, what sort of data quality would you need to really be able to start to break these degeneracies? Is the ELT going to be good enough to really distinguish between these models, or if there's combinations of these models at play? How far can we really push it?
So there's two things that we should, I think, disentangle here, which I didn't mention in the talk. So the first thing is, how can we distinguish between these different models? That will always be in some form difficult, because some of these models basically fit to the data with a chi-square and then say, okay, these parameters for my model fit really well, and then it's up to everybody in the community to decide whether that makes physical sense. So what I do for the radial wind is that I do a nested sampling retrieval, so at least I can distinguish between different wind patterns, and I can distinguish between no wind at all, which is already a step forward. Well, we were hoping for Oza and I, so Apurva Oza, who's like the mastermind behind this optically thin torus idea, that we combine these two with the same nested sampling retrieval algorithm, so that via the Bayesian evidence, we can actually compare the fit between these two ideas. So I think this is like the theoretical, like statistical step that we need to do, that all models that we want to compare use the same metric. And then on the other hand, there's obviously the question of how good is the data? In the Bayesian analysis, the error in the data set is taken into account. So you just get very large error bars of the data set is quite bad. So this is, for example, here, when you look at my 2020 paper, the errors on the wind speeds are huge. We can basically only say something about which wind pattern is best, but not really which wind speed. Whereas the wind speeds for WASP 76, we can actually distinguish quite well. So I think here the ELT will really, really help us out. But on the other hand, a few of these things are just intrinsically degenerate. So for example, a wind in the lower atmosphere that carries material from one side to the other will automatically be degenerate with a temperature profile that could do the same thing. So whether I retrieve a very strong temperature gradient between the day and the night side, or whether I use a wind to produce the same thing, it will look very similar or basically the same. So this is where you need a more theoretical approach. So this is why I said we give kind of the observational framework. So I'd say this is like the wind speed that could explain this, and then it's up to theorists to tell me from first principles whether that makes physical sense. So this is why the Wardenier talk, I think tomorrow, is going to be super interesting, because he comes from the Oxford group that actually does this theoretical modeling and will tell us a little bit more about how the wind and the temperature can be degenerate and how we can possibly disentangle that. And for that, I'm not sure the ELT will help us. So I'll leave that to the theorists to tell us more about that later.
Thanks a lot.
I have a question from Michael. You want to ask it?
Yes, as we have time, I'll ask. So thanks. It's very, very nice to see what you can learn from these sodium doublets and about these hot Jupiters. So I don't know a lot about hot Jupiters and about what we can learn from
Nobody does.
sodium. But I wonder, so you tend to observe this sodium in many of these hot Jupiters, if not all of them. So I wonder what you can learn from, say, the scale height in the easiest sense, but you have more sophisticated things here also to throw in as a class of hot Jupiters. Is this dependent, say, on the, I don't know, on the mass ratio, on the distance, on the illumination, on whatsoever? So is there some statistics on what we, strength of sodium versus something or versus some other things?
Yeah, you can really see the planetary scientists come in. This is such an important question. I just don't think we're there yet, because the sample is still very small. I mean, I think I showed you over half of all the detections that we have so far. So it's still like small number statistics, but it's one of the most interesting things because I mean, spoiler alert, I'm currently working on a data set where we think we don't see sodium and it's an ultra-hot Jupiter. And then the question is obviously why? Where does the sodium and the others come from? Also because it technically should be ionized. Does that mean they're outgassing it just faster than it can be ionized? Does it come from a different source, for example? Like there's a lot of open questions that I think we'll be probably able to answer in a few years' time once we have a good sample of ultra-hot and hot Jupiters, and then we can really say something about when is there sodium, when we have different line ratios of sodium, because that means that the opacity of sodium will be different, which is linked to the scale height as well. So I think it's not as clear-cut as saying, oh, there's sodium in all ultra-hot Jupiters, that's just what they do. I think the answer will be more interesting than that. But yeah, you're welcome to join us because we're not there yet.
Thanks a lot.
I think it will be very interesting to, obviously, once we have the numbers to do statistics, to start kind of putting all of these atmospheres also in the context of the primordial protoplanetary disk from which these things are formed, and start obviously looking at ALMA observations of similar types that lead to similar kind of stellar types. But yeah, I think, as you say, it's just we don't have this enough data to do statistics. And
also maybe did they migrate or not? Like obviously ultra-hot Jupiters probably migrated, but if one of them is completely different, does that mean it didn't migrate? Does it come from a different part of the disk and stuff like that? I think this is going to be really, really interesting. So I'm waiting for the larger surveys to do this. Like once NURBS and CRIRIS and we have all of this new power coming online in the next few years, I think it's going to move really fast. very excited.
Sure. Okay, we are almost out of time now, so I think we can move on to the next speaker. But thank you so much, Julia, for this brilliant start to the conference.
Thank you for the invite.
And actually, so before we move on to the next talk, I just wanted to mention that we have tried as much as we can to also incorporate talks from our colleagues that work on our own solar system. And sometimes we actually forget how much knowledge already is there, because I mean, the exoplanet field is very, very young, and we've really just started in the last 20 years, whereas they have another century or so head start on us. So we have tried to incorporate in both invited and contributor talks that are coming from our solar system, and that's in fact what we have now. So our next speaker is Henrik Malin from University of Leicester, and he's going to talk to us about atmospheres of Uranus and Neptune, if I'm not mistaken, right?
That's right.
Correct, the upper atmosphere of those two. So please, Henrik, it's yours. Please start sharing.
Can you see that?
Yes, excellent.
Great. All right. Thank you very much. I really do appreciate it. So I'm going to talk about Uranus and Neptune. Of course, these are the two planets that we know the least about in our solar system. So there's an interesting contrast there. So we have here a movie taken with the guide camera on IRTF iShell in 2019 of Uranus, and sort of a bit of a tour of the Uranus system. You can see the planet, of course, with a bright southern pole. It's driven by increased hazes at the pole. You can see the rings, and you have 3 moons orbiting the planet. There's also a dot moving from left to right, and actually that's a background, the galaxy in the background, basically, as Uranus is zipping through the solar system that's moving past the planet. Yes. The ice giants are, of course, Uranus and Neptune. They're far away from the sun, so 19 AU and 30 AU respectively. So they are very cold, dominated by hydrogen and helium, just like Jupiter and Saturn. They're about 4 times the size of the Earth. And on the left here, I'm showing the giant planets compared to Earth. And the solid line shows the orientation of the rotational axis, and the dashed line shows the orientation of the dipole axis. And what's interesting about the ice giants is that they have pretty weird magnetic fields. So for Uranus, who has a rotational axis inclined, sort of aligned with the ecliptic, and the magnetic field almost perpendicular from that. So a magnetic field that sort of flaps around every day. So a day on Uranus is 17 hours, and very similar for Neptune. And of course, this type of size and characteristic of a planet is not only observed in our solar system. We also see these types of sizes throughout the entire observable universe, should I say. Okay, so I just want to take a little bit of a step back, talked about centuries, and there's an interesting parallel between the discovery of Uranus and Neptune and the discovery of exoplanets. And that's because it's driven by human ingenuity and human invention. And so this guy, William Herschel, he discovered Uranus in 1781 in his backyard, and that's on the top left here. The backyard is in Bath, in the UK, and there's now a museum. You can actually go there, and I went, and it was pretty spectacular, you know, the wings of history and all that. So he worked very close with his sister Caroline, and they've made a number of discoveries together. So he discovered Uranus sort of by chance. He thought this fuzzy blob in the sky was actually a comet, but it was later confirmed to be a completely new planet. So this was a huge deal, right? This was the first planet to be discovered since the antiquities. Humans always had Mercury, Venus, Mars, Jupiter, and Saturn visible in the sky by the naked eye. And for the first time, we actually have a new planet, a new member of the solar system. And it made him an absolute superstar in the international community. And he got given money by King George III to build a 40-foot telescope in Slough. Slough, coincidentally now, is next to Heathrow Airport. so not the best place for astronomy. So this was the largest telescope in the world for about 50 years. So with Uranus having been discovered, they started plotting the orbit of Uranus, and eventually people sat down and started creating these astronomical almanacs that predicted where the planets would appear in the night sky. And I'm going to butcher some pronunciations here, so I'm sorry about that. This Alexis Bouvard, maybe, he made an almanac that predicted the positions of Jupiter, Saturn, and Uranus. And these predictions were really good for Jupiter and Saturn, but they were way off for Uranus. And so the question is why? And the leading theory was that there was another planet outside the orbit of Uranus, the new planet. And two guys with mathematical chops, Adams and Leverrier, made predictions based on the Bode's empirical law and Newtonian celestial mechanics to where would we find this planet based on the perturbations of Uranus's orbit. And this fella, John Gottfried Galle, discovered Neptune for the first time in 1846 at the Berlin Observatory. And he wrote to Galle wrote to Leverrier that the planet whose place you have computed really exists. So this obviously is a huge triumph for celestial mechanics and for the scientific method. Here people predicted the existence of this object before it was actually observed. So it's a really neat sort of saga of discovery. All right, enough of the history. So I'm going to talk about the upper atmosphere of the ice giants. And I'm going to provide some definitions, what I mean when I talk about the upper atmosphere. So the upper atmosphere is located above the line or surface, which is the homopause. The homopause is where the molecular diffusion equals the eddy diffusion. So it's the boundary at which the turbulent motion of the atmosphere gives in basically to the distribution of the molecules according to their molecular weight, essentially scale height. And this means that heavy species fall out really fast in the upper atmosphere. So at the homopause, at Uranus and Neptune, we have lots of methane and things like that. And the rest of the upper atmosphere is dominated by molecular hydrogen and helium. So this obviously generates a low density atmosphere. The upper atmosphere has two principal components. We have the neutral thermosphere, which is the H2 and helium. And we have the charged particle ionosphere, so a weakly ionized plasma produced via ionization from the sun and ionization by auroral processes. Within the ionosphere, the molecular ion Hu+ is a dominant ion, and we can observe emissions from this ion using near-infrared spectrographs. And like Julia, I'm a massive fan of telescopes, and so in near-infrared as well. And this is a really powerful remote diagnostic of the physical conditions of the upper atmospheres in our solar system. So from these spectra, we can determine the temperature, ion densities, and radiative cooling rates, and things like that. Okay, so why should we even care about this 10 years upper atmosphere? Well, we make a contrast to the Earth here. Because the ionosphere is charged, it feels the magnetic field, and therefore becomes a critically important interface region between the atmosphere below and the magnetosphere beyond. And it's sensitive to the forces and processes that are present inside the magnetosphere. So it's the conduit, it's the interface layer between these two regions. And the plot on the right here shows you the immense detail at which we can characterize the ionosphere at the Earth. All these features are either connected to the magnetosphere or the lower atmosphere. And of course, we have nowhere near this kind of granular detail at the giant planets, but we expect these features to be present to some extent, or even perhaps with the greater ferocity. So basically all our fundamental understanding of Uranus and Neptune comes from the Voyager missions. Launched in 1977, there were two probes. Only Voyager 2 went to Uranus and Neptune. Uranus in 1986, and Neptune actually on this very day in 1989. So just to give you a perspective of how long ago this was, this font here is Comic Sans. And that was released by Microsoft in 1993. So this data is older than Comic Sans, and that's sort of a fundamental challenge. We really would like another mission, which is one of the luxuries we have of studying the solar system, I suppose. So this is the, sort of the basic atmospheric structure that Voyager 2 spacecraft derived from occultation measurements in the ultraviolet. These are not the best plots, but I've tried to put the vertical distance on the same scale here, and we can see that Uranus has an extended upper atmosphere, whereas Neptune has a more compact upper atmosphere. We're dominated here by helium, molecular hydrogen, and methane right at the bottom of the atmosphere. It's a little bit hard to read, but the temperature at the top of the atmosphere, that's the exobase, or the interface from the atmosphere to space, is 750 Kelvin for both planets. And if you're thinking that that sounds incredibly high, then you're absolutely right. These planets are really far away from the sun. How do these get so hot? And this is something, sort of a fundamental question we have in planetary science, and we have dramatically dubbed it the energy crisis. And here I'm showing you a table from Yella-Miller 2004. There's a number of parameters listed here, but we can calculate what the temperature of the upper atmosphere ought to be based on the solar input alone. And then we can actually take the measurements, and we will subtract one for the other. And we are left up with the energy, the temperature that's unaccounted for in the upper atmosphere. And as you can see, for Uranus and Neptune, we have hundreds and hundreds of kelvins that are essentially unaccounted for. And this is a serious problem. We fundamentally do not understand half of the atmospheres in our solar system, and by extension, any hydrogen-based atmosphere in our universe. So this is one of the things I'm focusing on. What could potentially be the solution to this energy crisis? Well, the first sort of postulated solution is auroral heating. I'm taking Jupiter as an example here, because we have some pretty fab data from Jupiter. So the idea here is we have the auroral process about the magnetic pole. This is where electrons get accelerated along the magnetic field lines. They impact the planet and are driven through the planet, colliding with its constituents and heating it by way of Joule heating. So this can inject several terawatts of energy about the magnetic poles, which is great for the poles. We can heat the poles, that's absolutely fine. But the energy crisis is present at all latitudes, so even at the equator. So how can we move this energy down? It turns out it's incredibly hard. A day on Jupiter is only 9 hours long, and that makes the Coriolis forces absolutely immense. So it's very, very difficult to move energy from the pole down to the equator. It has been suggested through the variable nature of Jupiter's aurora that we can drive packets of heat down to lower latitude. And we showed this in a paper this year. There might be some observational evidence for what is happening, but it's still very early days. The second mechanism is wave heating. And here we have the turbulent lower atmosphere. Here we have the Great Red Spot, which is the biggest storm in the solar system. It's larger than the Earth, and it's been around for more than 300 years. It should be a great source for these gravity waves. They propagate up in the atmosphere into the upper atmosphere, where they break and they release their energy. It is somewhat unclear at this point how much energy is available through this process, but we have observed this again exactly once above the Great Red Spot, where we observed the ionosphere to be the hottest, hotter than anywhere else on the planet. So these mechanisms could be in play for both Uranus and Neptune as well, but our understanding of the ionosphere, global ionosphere of these planets is indeed very vague. Okay, so going back to the auroral sort of hypothesis, again, the observations of aurora at Uranus and Neptune is scant, to say the least. This is Voyager 2 observations on the left, These dots are auroral emissions in the ultraviolet, and I've mapped them here to a sphere during equinox conditions, and that was 2007. Similar sort of observations have been done by the Hubble Space Telescope, where we basically see a dot of emission, which is very different. If you remember the movie of Jupiter's aurora I saw earlier, which is quite dramatic. So what's interesting here, because of the offset of the magnetic field to the rotational axis, the aurora actually occurs on the equator at Uranus, and this could potentially make it easier to solve the energy crisis at Uranus. But then again, we don't know much about the aurora itself, how much energy is available through that process. And lastly, at Neptune on the right here, we have basically maybe a detection of some UV emissions that could be auroral, perhaps. So it's a very basic chemistry of the upper atmosphere of Uranus and Neptune. We have a hydrogen, molecular hydrogen atmosphere, and we have energy being injected into that atmosphere, either solar photons or energetic electrons delivered via the auroral process. So that can do one or two things. It can excite the constituents of the atmosphere, and the excitation of H2 and H produces observable emissions in the ultraviolet that can be observed with, for example, Hubble or a spacecraft, a different spacecraft. Via the ionization process, H2 is produced, and is very quickly converted to H3+, which emits in the infrared. And also we have quadrupole H2 emissions also available in the infrared. So H2+ is produced via this reaction. It's extremely fast. So any H2+ ions will be very quickly converted to H3+. So the intensity is driven by this equation here, and doesn't really matter what these constants are, but it's driven linearly by number density and exponentially by temperature. That's all we need to know at this point. We lose H2+ by recombination with electrons and recombination with heavy stuff like methane. And that means H2+ cannot coexist with the methane that sits at the bottom of the homopause, for example. If you want to have a go at generating your own H3+ spectrum, I've created a Python package that can do that. So you can generate the spectrum for your favorite upper atmosphere, favorite planet. Simple pip install, and that's the URL if you want to have a look. And here's some examples. It can also model quadrupole H2 emissions if that is your jam. Okay, so H2+ is observable from the Earth, so ground-based near-infrared facilities, for example. And here's sort of the relative sizes of these planets, the giant planets from the Earth. Jupiter is a wonderful target to observe. We have an object that's about 50 arcseconds in size. Then we have Saturn. The rings are sort of the angular size of the disk of Jupiter. And then we get down to the small stuff. So Uranus is 3.7 arcseconds in the sky-ish. Neptune is something 2.5 arcseconds. So compared to Jupiter, Uranus and Neptune are hard to do. And of course, exoplanets is a different thing altogether. So we can do, so on the bottom left here, we have auroral mapping using, this is VLT Cryonis by Johnson and al. And we can actually measure ion winds in the atmosphere using the high resolution spectrograph. With Keck Nearspec, you can also map the aurora of Saturn. And with Gemini Neary, we can map H2+, the disk of Uranus in H2+. Now, Neptune has always been a challenge. We've never observed H2+ from Neptune. Well, I'll come back to that because it's a real quandary and an interesting one as well. So Uranus, the first detection of H2+ from Uranus was in 1993, and this is the sort of discovery spectrum using UCERT, a telescope no longer owned by the UK. It derived a temperature of about 740 Kelvin, again, very hot, too hot, in fact, for our current understanding. And that's very similar to the 750 Kelvin exospheric temperature derived by Voyager 2. Since this discovery, there's been a number of sort of sporadic observations of Uranus up until 2009. And so what I did, I wanted to investigate what the long-term variability in the upper atmosphere of Uranus was, something we really not had a handle on. And this is the first result. So I reanalyzed all the spectra and derived the globally average temperature, and I plotted that as a function of time. That's on the left here. Temperature versus time, that's the points with the error bars. The dotted line is a 10.7 centimeter flux, and that's a proxy for the solar flux, the solar cycle variations. And I was hoping maybe to see a correlation with solar cycles. The more intense the radiation from the sun, the more He+ you produce, and potentially the more heating you have. But there was no such correlation at all. The dashed line shows you, it hasn't got a scale, but it shows you the subsolar latitude, which is a proxy for season. So we had an equinox in 2007. The previous solstice was when Voyager 2 was there in 1986. And we had the next solstice in 2028 or something like that. And so what's really interesting about this, of course, that we see a long-term cooling trend. And in fact, I titled this paper long-term seasonal variability of the upper atmosphere of Uranus, emphasizing the seasonal, which was perhaps in retrospect a bit of a mistake. On the right here, we have a table just again to highlight the energy crisis. So the run number is the individual observation. We have the year, the solar input based on the 10.7 centimeter flux in gigawatts, and then we have the He+ cooling. So He+ is a really efficient emitter, and so it radiates away energy from a particular region quite easily. And so we see that the energy radiated by He+ is way larger than the solar input. So the solar input is only 10% what He+ radiates away. And this again highlights the energy crisis. Where is this energy coming from? So what I wanted to do then, of course, is to extend this study. This ended in 2000, it was data from 2009. Yeah, 2009. So I sort of kickstarted this new program to provide regular observations of Uranus throughout the 2010s and into the future. And so we used a number of telescopes here. We have iShell on the IRTF. And all these plots show you intensity as a function of wavelength, essentially. So iShell, we have NERSPEC on Keck 2, GNERS on Gemini, SPECS on IRTF, and CRIRES on VLT. And so with all of these instruments, with different spectral resolution, we can really resolve these He+ lines. We can fit a temperature and density to them, and then we can plot that as a function of time. In total, we had 47 nights between 2011 and 2018. Of course, this program is continuing right now. I haven't got a direct update for you yet. So plotting all the individual observations, then temperature as a function of time, there's an interesting amount of scatter in this plot. It seems, if you look at 2011, for example, this region here, if you can see my pointer, the scatter is enormous. And sort of my feeling of why this scatter happens, it feels like it must be a variability in the auroral process. So the amount of energy that the aurora can inject into the atmosphere changes over time. And of course, if you look at this, there's no clear trend. I think there's a couple of interesting years here. So 2014, sorry, can't see my pen, can you hear? 2014 and 2015 was only one data point, but they stand out as very hot. And this actually coincided with the emergence of a storm observed by Imke de Pater. So could this heating be related to the emergence of the storm generating gravity waves that heat the upper atmosphere? Maybe so. I then took the average per year and then plotted them as a function of time again. And it seems, if you average it per year, it seems like this cooling trend has continued. So we have almost 30 years, 3 decades of observations in 1992. And throughout this entire period, we observed to be observing cooling in the upper atmosphere. And that also means that the mechanism responsible for the energy crisis has changed over those 3 decades. Well, not the mechanism, but the ferocity of this mechanism, right? It's also interesting that 3 decades is longer than a season at Uranus. So it takes Uranus 84 years to go around the sun. So a season is 21 years. So this cooling is longer than a nominal season. One other interesting aspect of this, so I showed you a slide earlier where the intensity of HU plus is a function, exponential function of the temperature. So it's actually incredibly difficult to observe Uranus right now compared to when it was discovered in 1992. So as our instrumentation and telescopes have improved, it's sort of like Uranus is fighting back and become harder and harder to observe, which is slightly annoying if that's your job. Anyway, it's super interesting. So yes, I have some theories of why that is. So I have something called geometric season. You can think of this as being linked to heating by gravity waves generated by the lower atmosphere. So it's some kind of seasonal variability in the lower atmosphere driven by the extreme seasons we'll have at Uranus. And this is, by the way, some excellent clip art. We also have magnetic seasons, which is generated by, you sort of think of it as auroral heating. And so because of the magnetic field is highly tilted, offsets from the center, and contains strong octopole and quadrupole components, that means essentially that the geometry of the magnetic field with respect to the solar wind at the 2 equinoxes are not the same. And so you can envisage a scenario with a geometric season where you have two peaks each year in temperature, whereas the magnetic season you have 1 peak per year with some offset due to thermal insulation. And so I can't give you the answer right now because we need more observations going into the 2020s. And it's going to be really interesting what happens. And I really thought that the temperature would begin to go back up after 2009, 2006, after the equinox essentially. But it appears we're at a downward slope. And even now, early analysis of the new observations indicate that this cooling is continuing. We're down to sort of 400 Kelvin now, which is, yeah, a real challenge. Well, I got time. Okay, so a few quick words about Neptune then. So we've not discovered HU+ at Neptune, but if the models that exist, the very few models that exist of the atmosphere of Neptune are correct, predicting sort of a peak density of 100 per cubic centimeter, then we should be able to detect it with our existing instruments and ground-based telescopes. And so I've tried a couple of times to detect HU+ at Neptune. Firstly with Keck, I used NIRSpec. So the bottom at the top here, at the top plot, the bottom part of the top plot, we have a number of HU+ lines. So the vertical axis is spatial dimension and the horizontal axis is wavelength. So it's just centered on these emission lines of HU+. And even if you co-add it on the right there, Uranus is nice and bright in HU+, and there's absolutely nothing at Neptune. And same, did a deep 15-hour deep burn with iShell in 2018. So either the models are completely out, or, and this is an interesting idea, maybe Neptune is also cooling, which would be, yeah, it'd be quite odd. If Uranus is cooling and Neptune is cooling, why would that be? We're not like, you know, there's no real connection there. So there's a great paper by Luke Moore that discusses all of that. So the big question, of course, what is driving the energy crisis? And in the context of this particular meeting, is it unique to our solar system? I suspect it's not. I think any hydrogen-based sort of giant planet atmosphere might see this happening, and that's really interesting. Once we can are able to detect H2 plus or other ionospheric species in the upper atmosphere of these sort of ice giants, are they hot? What do we expect them to be? And also, I'm not going to go through this, but we need to detect H2 plus at Neptune. And of course, we have the James Webb Space Telescope being launched in November this year. It is the NIRSPEC instrument will be absolutely perfect for observing the ice giants with its 3.3 arc-second IFU. We have observations in place and a guaranteed time observing program to observe both Uranus and Neptune with NIRSPEC and MIRI, giving us sort of this 2 to 28 micron coverage of both planets, full mapping. So that will be absolutely stunning. And of course, we have the next generation 30-meter telescopes for which the ice giants are going to be absolutely excellent targets. So we've learned that the ionosphere is an important part of the atmosphere, and the upper atmosphere of Uranus has surprisingly been cooling for the last 3 decades, which is longer than a nominal season at the planet. It's sort of a unique data set, something we don't have for any other planet. We haven't seen H2 plus and Neptune yet, which is sad. And I'd like to advocate, maybe this is the wrong audience, but I'd like to advocate for a real mission, as sort of a L-class mission to Uranus, the ice giants. That'd be nice. Thanks.
Thank you very much, Henrik. Excellent talk. Yeah, questions. Floor is open for questions, comments. Do we have any hands up? Yes, we have a hands up from, I don't see whose hand. Oh, Julia, please.
Yeah, it's just me again. So I actually, it's more of an open question. So I find this whole energy crisis really fascinating, especially since one of the major issues that we have when we move to cooler planets in the exoplanet realm is that it's much harder to observe the atmospheric features because we don't have just like the resolved lines. It's molecules and molecules overlaying each other and clouds. So things get much harder. So if you think about like exoplanets and we think about Neptune-sized exoplanets, do you think that the heating mechanisms that you have proposed that might play a role in this energy crisis, do you think they could also play a role in Neptune-sized planets that are already kind of, let's call them warm? Or do you think it's only if they're truly like our Neptune that they'll have an impact on the heating?
Well, sort of the two solutions, or the two sort of proposed sources for energy for the energy crisis are the auroral process and gravity wave heating generated by the turbulent lower atmosphere. And those are sort of ubiquitous processes. You know, aurora requires a magnetic field. The majority of the planets in our solar system have magnetic fields. All planets have weather, but you need weather to generate these waves. So I think to some extent, these processes will be occurring, right? It's just a question of how efficient are they. So take the auroral process, for example. It works differently in different planets. So say Jupiter has this volcanic moon called Io that spews out a ton of material a second. And that creates an enormous fuel source for the aurora, whereas somewhere, say the Earth, is only dependent on the incoming solar wind. So it depends on the planet, what kind of resources, so plasma resources there are for these kind of processes. And for the sort of gravity wave heating, we need, so the higher the internal heat left after the formation of the planet, the more energy is available to drive the turbulent behavior of the atmosphere. So yeah, there's a number of parameters which, yeah, I don't know if we know of what those are at these exoplanets.
That's really cool. That opens up a whole new set of ideas for narrowband spectroscopy. Thank you so much.
You're welcome.
There is a question in the chat from Aaron. I don't know if you want to ask it or you want me to read it. He says, you talked about the need to go back to the ice giants. For some reason, if for some reason you could only choose one, which one would it be and why?
Ooh, that's a great question. It's like choosing one of your, which of your children is your favorite, right? People like to go to Neptune because of Triton, you know, the sort of captured Kuiper belt object. I think I would pick Uranus because I'm more familiar with it, and it has this extended atmosphere, so you could potentially do aerobraking to the orbit capture and stuff like that. It has a number of fascinating moons, and it has. We know there's Aurora, for example. We don't know anything about Neptune really, which could be a really good reason to go, I suppose. Yeah, just do one of each. That'd be good.
I have the question, and if there isn't any more in the chat, let me check now. Kind of two parts a little bit. First of all, I'm sorry, maybe if you said it and I missed it. Have you performed, at least for Jupiter and Saturn, have you performed a spatially resolved spectroscopy of these emission lines to see if in fact there is any dependence on the location? And because I guess you're saying that they are correlated with the strength of the auroral emission, also the magnetic field. Have you has this been done?
Well, it has. So one of my students is working on the Keck-Nersbeck data, where we actually map out the ionosphere for the first time at Uranus, which will be out hopefully within the year. But certainly for Jupiter and Saturn, we have almost complete maps of the ionosphere of these planets just by scanning a spectrograph. You know, in 25 seconds exposure on Jupiter, we can get a signal to noise of 30 or something, which is very pleasant.
So you do notice a strong correlation between obviously where you are spatially and where the strong magnetic fields are and the strength of these lines?
Yeah, absolutely.
So I was just wondering, maybe you showed this at the beginning of your talk, that maybe the orientation of the magnetic field in Neptune is not allowing for this to be seen. Could this be? The emissions to be seen?
Well, we should. So the ionosphere. So there's a global ionosphere produced by solar UV photons. So basically, it should be a disk, a glowing disk, and that's sort of. In addition to that, you have these spots or rings or arcs produced by the auroral process, governed by where the electrons hit the atmosphere. So where the feed lines connect into the atmosphere, where there's plasma available, essentially. Yeah. Neptune is a tricky one. Like there should be Aurora. Voyager 2 was like maybe. It's just too difficult right now. Yeah.
I'm guessing before, obviously, James Webb, you're going back to these with Criris Plus, no? Since it's coming back.
Yeah, that's the plan. When is that on? You must be an expert.
It's already on. It was offered in the last call.
Awesome.
You have another 3 weeks to write your proposal.
I'm not busy. Awesome. Thank you.
Great. Okay. I don't know if we still have a couple of minutes for further questions, discussions. If not, please feel free, obviously, to ask Henrik and all the other speakers of today to go to the Slack channel. They will be joining that channel to answer your question. Just make sure you add them in your talk. Thank you again, Henrik. That is excellent talk. Now we move on to contributor talks of this session. And the first contributor talk is from James Head from Brown University. James, please go ahead and share your screen.
All good there?
Yes, great, thank you.
Okay, and I prefer the questions at the end, and recording is okay, and I'll send along the PDF when I'm done.
Thank you very much.
Thank you very much for actually accepting this abstract. This is a little bit unusual for those of you old enough to remember Monty Python. This will be, in fact, and now for something entirely different in a way. It's also essentially, I worked in planetary geosciences for about 50 years. And so it's going to be my life flashing before your eyes too. So I hope this is helpful. And it's been a really exciting time, and we have great things going on in the future. So let me try to share that with you. Basically, let's go back to when I was in high school, pre-1959. Well, there's this big blob in the sky. What's that all about? What do we know about the moon? What do we not know? First of all, we didn't know its origin. We didn't know its age. We didn't know whether it had formed hot or cold. We didn't know the nature of the surface, the age of the surface, or even the origin of the craters. We take this for granted now, but a huge debate on their origin. And oh, by the way, what does the other half look like, the lunar far side? We didn't know. I mean, imagine that, okay? So in the last 60 years, we've learned a huge amount. But you know, when I had my freshman geology course, one of the first things we learned was the origin of the planets, and we looked at the Laplacian theory, essentially where temperature and pressure decreased as a distance from the proto nebula, and the collapsing solar nebula indeed explained, you know, predicted and explained many of the observations related to the characteristics of the planets, their distribution, and their physical properties. So seemed like a good idea to me, worked really well. Okay, onward and upward. So I went on to geology in detail. In the last 60 years, we've really had two fundamental revolutions in our understanding, really fundamental. The first one had to do with global plate tectonics. This is something that is more in the geological realm, but basically planetary exploration put the Earth in a context, which is, it's a planet, folks, okay? Planetary geosciences belongs in geology, not astronomy, as it began to be known. And oh, by the way, you geologists, the Earth is a planet, okay? And oh, there's a bunch of other ones out there we can learn from. And then, of course, the space age. We learned about the Earth in the context of the solar system. So these two perceptions really revolutionized our thinking in so many different ways. And basically, in this 60 years of solar system exploration, you know, planets have changed from really astronomical objects to geological objects. And the good news here is not that we've diverged, but that we're coming back together with exoplanets. And that's what I want to try to do today, is to provide some basic background here. We've actually sent geologists to the moon, for crying out loud. We had 6 very successful Apollo missions. And indeed, the Apollo missions were, in fact, a fundamental key to our understanding of exoplanets, that is planets, I'm sorry, I should say just planets other than the Earth. So this is just a summary slide, the topic slide, title slide that I did for an invited talk to the AAS a couple of years ago, in which we talked about this. It's not just about Apollo 11. In fact, the legacy of Apollo is 6 successful exploration missions. Apollo 15, 16, and 17 were scientific expeditions to the moon. They had rovers. They traveled 30 kilometers. They picked up hundreds of kilograms of samples. They did sustained geological exploration. There is a legacy that is indeed the cornerstone for understanding the planets. And what do we learn from this? Well, first of all, you know, from my colleagues in the geology department, oh, by the way, what's the origin? I remember in my freshman geology class, we studied the Phanerozoic, which is the last 5% of the history. And then I said, well, what about the rest of it? And, well, we don't really know that much about it. Why is that? If we take a look at the history of a planet in the context of a clock, where it starts here at the beginning and works around to today, the percentage of the surface that's preserved from each of these times, the ocean basins, 60% of the surface, is less than a few percent of the planet's age. And then the rest of this is continents. But the first half of solar system history, we're literally clueless about what was actually going on in detail. And of course, what we learned is that the moon is the laboratory for the study of this. It really gives us insight into those missing chapters in Earth history. So that's absolutely amazing. I mean, just amazing when you think about it, okay? So this is why planetary exploration is so important. Furthermore, we can take a look at the characteristics of planetary bodies and test some fundamental hypotheses, including the Laplacian hypothesis for the solar nebula collapse in an orderly fashion. So we can look at planets in terms of their position in a solar system, their distance from the Earth, shown here. We can look at them in terms of their size. What's the role of size in planetary evolution? And so this is what we set about doing in the last 60 plus years. And in fact, I want to review here some findings and surprises, which I hope will be useful in exoplanetary exploration. Let me just touch on a couple of these here to try to illustrate this. And again, my email is at the end. I would love to communicate with any and all of you about this because we are entering an era of comparative planetary systems from which we can learn from each other in so many different ways, as you just saw from the previous discussions and the two great keynote talks. So planetary formation and early evolution, what have we learned about that? Well, actually, Laplace, by the way, planets are moving around in early solar system history. Jupiter's moving around, other things are moving around. By the way, when they do that, they send big pulses of projectiles into the inner solar system. Could we have a late heavy bombardment here? How did that influence life on the Earth? How did it influence life on the other planetary bodies if it existed? In the outer solar system, there's so much going on that influences the inner solar system, and it's not a simple picture. Oh, by the way, the origin of the moon, the giant impact hypothesis. The moon, as most of you know, is thought to have formed by the impact of a Mars-sized object, 1/2 the diameter of the Earth, into the proto-Earth, and the early Earth. And the ejecta from that is what is believed to have formed the moon, gone into orbit around the Earth and accreted to form the moon. This is pretty interesting from the point of view of exoplanets. Now, of course, we're dealing with resolutions here, which won't be available for a while. James Webb will help, but nonetheless, you should keep these things in mind. So stochastic processes begin to really, wow, that's interesting. That had a, if you talk about trying to understand planetary evolution, it's really important to think about, in a way, planets as humans. If I wanted to understand any one of you, I would want to know what happened in your childhood. But of course, what were the traumatic events? What was your environment, et cetera, et cetera? Well, let me just tell you that this is a traumatic event for the early Earth. It never was the same. So, if that happened on any exoplanet, it's a definitely fork in the road in terms of its evolution. So stochastic processes are really critical. What about the formation and evolution of planetary crusts? Well, first of all, we see from the data from the moon and other planetary bodies that there are 3 types of crust. Primary, formed by accretional energy and essentially melting of the outer part of the planet. This is kind of like the lunar crust, the lunar and orthocity crust. And then subsequent to that time, as the interior heats up, basically we get secondary crust, which is derived from partial melting of the mantle and extrusion out on the surface. If the planet is really dynamic like the Earth, we get tertiary crust, which is formed from recycling of primary and secondary crust. So again, when you think about exoplanets in particular, they could have had a very significant evolution in the context of the formation and evolution of primary, secondary, and tertiary crust. For example, if we see that in fact a heavily cratered crust on the moon, whereas on Mars, it's pretty much dominated by secondary crust, and on the Earth, basically tertiary crust is indeed what formed the continents, about 30% of the surface of the Earth. The second thing is tectonic systems and heat loss mechanisms. If we take a look at this diagram here, which is basically taking a look at heat loss mechanisms, we know that the smaller terrestrial planets, Mercury, Moon, and Mars, 1/2 the diameter of the Earth or less, lose heat by conduction. Okay, so they basically stabilize their surfaces early on. On the other hand, a planet twice that diameter, like the Earth, has a plate recycling system and also loses heat from radioactive material sequestered in the crust by tertiary crust formation. And then we go over here and we have essentially EO, the innermost of the Galilean satellites, which loses its heat by volcanic heat pipes, by advective heat transfer. And there's no single impact crater seen on EO because it's resurfaced so fast that they're all buried. That's incredible. Okay, so we need to keep these things in mind as well. What about the role of size in planetary evolution? Well, if we take a look at this, this is where we were prior to about early 80s, okay? Again, time, I'm a geologist, time doesn't kick in until about 20 million years, so sorry on the short-term time. So we have here, this is a diagram of the origin of the planets to the present with a percentage of the surface area formed at different times. So we have the Moon, Mercury, and Mars, crust formed early on, secondary crust formation, not much happening on the last half of solar system history, whereas the Earth is really dynamic. What about Venus? We know that Venus is, in fact, about the same size and position in the solar system as the Earth. That was what propelled us to do a lot of Venus missions to try to figure out where it fit in this context. And what did we find? Did size not make a lot of difference? Maybe it was like the Moon, Mercury, and Mars with lots of craters, or did it have plate tectonics like the Earth? What do we find? The Magellan mission back showed that the surface of Venus was largely formed in the last 500 million years. Okay, that's great. Okay, it's like the Earth. But wait, there was no plate tectonics. How the hell does that happen? Okay, well, I have to say that since the 1990s, okay, there have been 6 at least major theories for the transition from an early to late history of Venus. And we don't know which it is. That's why these 3 Venus missions, which have just been approved by NASA, well, 4 actually, NASA, ESA, and Roscosmos, will really be important in trying to sort this out. So this is a big mystery. How do you get an Earth-sized object that's totally resurfaced in the last few hundreds of millions of years? I mean, when you think about it, Earth is pretty stable. Well, maybe not. We better figure this out. Internal structural and mantle convection and petrogenetic evolution. This is really important. We've learned so much about this. We're a prisoner of the Earth model of the interior, and we've learned a lot since that time. Going back to the Laplacian, let's go to the innermost planet of the terrestrial planets, Mercury. It's so close to the sun that the temperature and pressure distribution in the collapsing solar nebula must have driven all the gas, all the volatiles out here and concentrated the iron core. It is indeed 1/3 the size of the Earth, but has the same density. And when we look at the internal structure, we know the reason for that, okay? There's a huge core. But wait, MESSENGER showed that there were volatiles. We see explosive volcanic activity. You can see it in the orange areas around the Caloris Basin here. So whoop, wait a minute, back to the drawing board. It's got volatiles, folks. Secondly, the structure, okay, here's the Earth. 1/2 of the Earth is a liquid outer core, is a core, okay? On the other hand, more than 70 or 80% of the surface of the interior of Mercury is a core, okay? This means that the mantle convection and the mantle characteristics are way different than what we see on the Earth. The oxygen fugacity of the mantle, we're struggling with this, doing experiments in the lab, et cetera. And also the characteristics of the surface, the volcanism is totally different than what we see on the other terrestrial planets. Not only that, we see these huge scarps related to the evolution of this incredible large core and this unusual mantle. Big lessons here, okay? What about planetary processes here? Well, we've learned a huge amount about this. The moon is a fundamental laboratory for the study of impact cratering processes. Now, you say, oh, good, there's a lot of them, lots to do, career here, no problem. But the key here is, in planetary atmospheres, impacts giveth and they taketh away. Okay, they giveth because they bring in volatiles. We're even arguing right now whether we can get enough volatiles coming into the moon from either impact cratering or, in fact, from volcanism to produce a transient atmosphere that might have lasted 80 or 100 million years on the moon, for crying out loud. And not only that, but the big impacts could actually take away the primary atmosphere. And then you have left what you get from the interior. So impact cratering and transition from primary to secondary atmospheres is critically important, which leads us to planetary atmospheres. And I can say right now that we have a lot of really exciting debates going on. Venus in particular, does Venus have today a recent or fossil atmosphere? Bullock and Grenspoon, Way and Del Genio, and others have argued that Venus, being so close to the Earth and also in terms of position in the solar system as well as size and density, underwent a distinctive Earth-like period for the majority of its history, and then transition in the latest period here to, in fact, what we see today, which is a CO2, let's just say hot and extremely dense atmosphere. Okay, 100 bars, blah blah blah. Okay, so that's a really interesting idea. Okay, is it in fact recent? And of course, we've looked at this and done inverse modeling from the geological record, and we suggest that the current atmosphere is actually a fossil atmosphere. It's very hard to get, with a dense atmosphere, volatiles out of the magma that comes out of the rocks because it suppresses it until it's, so we have a big debate here. And, you're probably familiar with the faint young sun problem on the Earth. If the sun was 70% of its current luminosity on the Earth, then, how do we get oceans on the surface, et cetera? That's been an enigma. There's lots of ways to maybe get around that, et cetera. But fast forward, take a warp speed 9 out to Mars, it's further from the sun, folks, and we're having the same argument. We see lots of evidence for valley networks, maybe oceans, maybe we certainly see open and closed basin lakes. The Jezero crater, Paleo Lake, is being explored by Perseverance as we speak. And just to think, if you think that's not a difference here, take a look at this. This is a warm and wet early Mars with extensive oceans. Here is something we've been doing in our models of the climate, where the atmosphere is not only with a faint young sun, about mean annual temperature of about 226 K, but it also has an adiabatic cooling effect because it's denser, and therefore we have a cold and icy early Mars with, in fact, all the ice in the highlands, and we derive evidence for their melting from transient events that melt the ice. So this is another debate, okay? There are also spin axis orbital parameter variations, okay? This is clear, okay? You can see here in this paper we did in 2003 in Nature that, in fact, you know, as we just heard, I mean, planets have variations in obliquity. So when you're looking at something at a given point in time, their atmospheres may be also related to obliquity variations, a really important parameter. So geological history and habitability. We take a look at Mars, for example. Maybe it was warm and wet. Okay, we're still fighting this battle here, transitioning to a present cold and icy. But the key here is we're looking in the subsurface now. Huge amount of effort is being dedicated to looking in the subsurface because it's warm enough and wet enough in the subsurface, for sure, due to heating from the interior, to create environments in which life might have formed. So again, lots of different ideas here. And as we go back to what I learned in my freshman class in geology many years ago, in fact, we could just take some perspectives and caveats here as I lurch towards a conclusion, which is terracentrism. You know, Rodney Brooks has this thing, you know, it's only been 400 years, but since we were the center of the cosmos, for crying out loud, he talks about a retreat from specialness and he calls it a route from specialness. We've got to keep that in mind. We always want to make ourselves special. Geologists have a particular problem in the sense that we have to we wean for 200 years away from the catastrophic biblical flood, okay? So this is uniformitarianism has become the gospel of geology. But, okay, the planetary science has shown us the role of stochastic processes. Oh my gosh, okay. I mean, yeah, uniformitarianism, which means basically the processes work over long periods of time. The stochastic processes are really critical, really, really critical. And we all need to keep that in mind. Paradigms, again, you know, the Laplacian paradigm, look good to me as a freshman, but we've seen that it's much more complicated than that. So again, the promise, but also the pitfalls of paradigms. And again, this space-time continuum, okay, we're all huddled around here listening to this talk, but basically geologists and astronomers are out here in millions to billions of years and miles and kilometers, okay? We have a lot to say together, okay? And I would say the last thing is when we were exploring Venus for the with Magellan, Tom Magetchan, my colleague, said, okay, it could be A, could be B, could be C, but don't forget D, none of the above. That's exactly what it turned out to be. So solar system comparative planetology, we have many fundamental questions that remain. Very exciting, very exciting. And these answers lie in the next 60 years of solar system exploration, but more importantly, they lie in the new era of comparative planetary systems around other stars. About 5 years ago or so, Stephen Kane came to me and says, Jim, I've got 50 Venuses. What do I do with them? Whoa, whoa. Okay, you're talking to the right person here. It's like incredible. So we're actually working on Venus as a laboratory for exoplanetary science. We published papers on this, and it's a very, very interesting thing to do. It's really helped us to get this perspective. And finally, really the era of comparative planetary systems. This is an era of collaboration between astronomers and planetary geoscientists. And again, 4,801 new exoplanets as of the start of this month. And again, I love the Einstein quote at the advent of the nuclear age, everything has changed but our way of thinking. I'm probably the only one in this conference that actually knew James Webb. I just want to say that this is going to be revolutionary. Don't forget to honor the person. He had the vision to get exactly where we are today. So please keep that in mind as you start your new discoveries with James Webb. So let's play marbles together, okay? I think if we can get some community cooperation here for our community, basically untold numbers of individual examples of planets and satellites, et cetera. Huge parameter space is yet another framework for our understanding. And the exoplanet perspective really helps us to develop future solar system exploration strategies, as you just heard from Henrik. The exoplanetary community, you know, I hope this provides a rich and accessible record of the origin, evolution, and fate of a small number, but really important views. And the lessons learned, I hope provides a template for exploring and understanding other planets and planetary systems. So I will just say here that please give me a buzz on email or any other way. And I hope this has been helpful in making some connections. Thank you very much.
Thank you so much. That was a brilliant journey in just 15 minutes. I open the floor for questions, comments. There is Julia.
Yeah, thank you so much. I think I've seldomly learned so much in 15 minutes in my life. I have actually a question, because I was rather recently disabused of the notion that, oh, why do we even care about geology for exoplanets? We'll never see the surface. So my question for you would be, what do you think is going to be, apart from the statistical approach to exoplanetary science, what do you think is going to be one of the first surface processes that we might see? Do you think it's going to be just outgassing from the surface, or volcanoes, or an impact from one of the moons, and we're going to see the scattering field, or some moon outgassing? There's so many options. What do you think is going to be the first thing we're going to see with our spectrographs for exoplanets?
Well, I think the key is obviously in the atmospheres at this point. That'll change with time, but that's where it is. And I think one thing to look for is something we've been struggling with on Venus, which is there's evidence for changes in the chemistry of the atmosphere over relatively short times, measured in terms of decades. And so trying to understand, searching for changes in the atmosphere, we see geological evidence, for example, for recent volcanic activity. We see with the Venus Express thermal instrument, Bertus, that there appears to be a time when the surface locally in a rift zone is hot, and then later on it's not, over the course of a couple of years. And that's a place where we see what look to be relatively recent lava flows. So, in those cases, we should see variations in the atmospheric characteristics. This can be correlated, for example, with, so if we know something about the composition and density of the atmosphere, explosive eruptions that take a lot of gas up into the atmosphere, like Mount St. Helens on the Earth, are very difficult with a very, very dense atmosphere like Venus, okay? Because the atmospheric pressure suppresses the volatile exsolution. But so, the combined distribution of, like, what are we finding here, there, looking for changes, I think that's the key. And, again, this is a good question. I haven't, I've thought about that, but I need to sit down and really think about it, okay? And I would love to come back maybe at a future time and try to bridge that gap, because it's only asking these questions and talking to each other that will get the perspective that we can actually answer the questions. So thanks, great question, thank you.
Thank you. Well, I'm looking forward to it. Thankfully, the exoplanet field is still very young, so we can wait a few decades and do the comparison.
I apologize for my ignorance, and I feel ashamed that I didn't know that the surface of Venus was in fact formed so recently. Could you maybe quickly explain how this was actually found out? How did we figure out that in fact the surface was formed so recently?
Yes, it's done. So we have samples from the moon where we know the place of them, so we can calibrate the impact crater size frequency distribution. The longer the surface of lava flow has been on the surface, the more craters it collects. So with Magellan, we got global data at a resolution sufficient to count, craters larger than a kilometer in diameter. There's a filtering effect from the Venus atmosphere, but nonetheless, you can account for that. And basically, there's only about 1,000 craters that we found on the surface of Venus. And Venus, again, has an Earth-like area in terms of its surface. So that age, it's again, not 100% certain, but it's certainly in the last billion years, probably in the last few 100 million years that the average age of Venus is. And then we don't see any variations in the craters, like, oh, these are degraded, these have been embayed. It looks like the surface was resurfaced and then craters started accumulating. That's kind of scary. The whole planet gets resurfaced. We have some models for that, like I illustrated, but it's only going to be with these upcoming missions from 4 different agencies that we're actually going to be able to test those ideas. So it's very exciting. And again, a lot has to do with the evolution of the atmosphere. The work we're doing right now, is it a primary atmosphere or is it a fossil atmosphere, or a late stage atmosphere that we see today derived from an Earth-like atmosphere early on? Or is it in fact always been this way? Our data suggests it was a fossil atmosphere But fossils go back a long way. So it might only go back halfway. So these are the kind of questions we're asking too. And that's how we got the age.
Great. Thank you so much. I think we have to move on. Really appreciate the talk. Okay, we move to the very last talk of the session from Emma Esparza-Borges from the IAC in Tenerife. And she will talk to us about retrieving transmission spectrum of HD209 using chocolate, a new chromatic DT technique. Emma, please start sharing.
Yes, I can't share because I had to leave the previous session because my pointer suddenly disappeared. So something was going on. Okay, I think now I can.
Yeah.
Let's try. Okay, so let's present. Okay, can you see it?
Yes.
Nice. Okay, so good afternoon and good morning, everyone. I am Emma Esparza-Borges, and I am going to present you my master thesis project, which is called Retrieving the Transmission Spectrum of HD209 using chocolate, which is a new chromatic line profile tomography technique. This project was supervised by Dr. Mahmoud Reza Shah and Dr. Henrik Malin. First, I will introduce some concepts that are essential to understand the methods followed in this project. Then I will explain an outline of the project as well as some details in each step of the methodology that we followed. And finally, I will present you the results and the conclusions of the project. In this project, we work with the CCFs, or cross-correlation functions of the spectra. As you may know, the cross-correlation function, or CCF, is the resulting function from the cross-correlation of a spectrum with a binary mask. And it measures the degree of similarity between the spectrum and the mask along a range of radial velocities. Also, the CCF can be understood as an average line of the spectrum with higher signal-to-noise. And the CCF is one of the main methods to measure radial velocity. When a planet transits its host star, it introduces anomalies in the CCFs, producing a bump. As the transiting planet moves across the stellar disk, this bump will move across the CCF, and the morphology of the CCF will change during transit. In this way, line profile tomography is based on the analysis of temporal sequences of CCFs, and it is able to relate the anomalies during transit in the CCFs to the planet-star radius ratio. And the use of line profile tomography method in different wavelength ranges leads to what we call chromatic line profile tomography method. In this way, chocolate method allows to obtain transmission spectroscopy using chromatic line profile tomography. So, summarizing, our chocolate method is based on the spectral line distortions produced by the planet during its transit in front of its host star. And we work with the cross-correlation functions of the spectra that reflect the line profile distortions during transit. So I will briefly explain an outline of our project. In this work, we aim to use chromatic line profile tomography method in order to obtain transmission spectroscopy. And the main objective of our project is to obtain a functional model of chromatic line profile tomography, extending the SOAP tool code that I will describe in detail later. In order to achieve this main objective, we produced Python scripts to reduce and prepare the data from express observations for a chromatic fitting procedure to test if our model is good enough. And this fitting procedure is MCMC based, and it should be able to estimate the planet radius in different wavelength ranges. We chose the planet HD209 to test our methodology because it is a well-studied exoplanet for its atmosphere and have already been studied by other methods. For this reason, we applied the fitting procedure to HD209 data as a reliability test of our model and to check if it is possible to retrieve the transmission spectra using chocolate method. In this project, we work with 2 full transit datasets of HC209 from Espresso spectrograph at the Very Large Telescope in Paranal Observatory in Chile. And these are the steps that we followed for the treatment of the data. First, we normalized each CCF, dividing by a second-order polynomial that was fitted to the continuum region of each CCF. Then we performed the Keplerian motion subtraction. Here we shift each CCF to the stellar frame of rest of the star, and we introduce to do this an offset in radial velocity in order to leave only the imprint of the rotation motion of the star in radial velocity. In the third step, we define 8th-order wavelength beams, and in the fourth step, we generate the master CCF as the average of the normalized CCFs from out-of-transit epochs. And we do this in each beam. So here you can see some examples of our master CCFs for different wavelength beams that you can see their centers here in nanometers. And the gray arrows that you can see here indicate the region of the continuum of the CCF that was used to normalize them. Then we subtract the master CCF to each normalized CCF in each wavelength beam, obtaining what we call the residual CCFs. Here you can see some examples of residual CCFs for different stages of the observations. Note that the in-transit stage show significant residuals, while the out-of-transit stage show plain residuals. And finally, we estimate the noise in each beam as the standard deviations of the regions far from the anomalies that we indicate here as the line-filled rectangles. So now let's go with the model. For the development of the model, we use a version of SOAP that is a software tool that simulates the effect of stellar spots and plates on radial velocity and photometry. It is able to simulate the radial velocity variations and also the light curves for systems consisting of a rotating spotted star with a transiting planet. We used this code to generate line profile tomography models from the output CCFs that SOAP produce. And this output depends on the SOAP input parameters that are fixed in a configuration file previously. Also, to generate the models, we need to fit SOAP CCFs to master CCF in each wavelength beam. And in order to be able to compare the models with the observations in the fitting procedure, we also apply the steps 4 and 5 to obtain the residual matrix from the models. For the fitting, we used an MCMC procedure. Specifically, we used the MC Python approach. We fixed all the input parameters in SOAP configuration file except the planet-star radius ratio and the limb darkening coefficients, which were all left free during the fitting. We also imposed a wide uniform prior on the planet-star radius ratio and Gaussian priors on the limb darkening coefficients. These Gaussian priors were centered on the LDTK estimations of the limb darkening coefficients in each wavelength beam. And here you can see a comparison between a residual matrix from the observations in a beam on the left. Then you can see on the center the best model from the fitting. And on the right, you can see the residuals from the fitting for this certain beam. And finally, here I am presenting the transmission spectra that we obtained through chocolate methodology, which you can see on the green circles. Here in this plot, you can also see in black Santos et al. Results, which were obtained from the same Espresso dataset that we used, but using chromatic Rositer-McLaughlin method instead. And in light gray, you can see Singh et al. Results that were obtained using multiband photometry of Hubble Space Telescope data. And as you can see, there is a good agreement between our results and both Santos and Singh results. And finally, I am going directly to summarize the conclusions of our project. First, as I have explained, we developed a chocolate method that is based on the physical modeling of observational data using the SOAP tool code. We validated its performance on HD209 data as a reliability test, and we obtained the transmission spectrum from chocolate methodology, and we observed that our results agree with previous results, like Singh et al., Santos et al., and we obtained similar precision than them using similar data and different methodology. And as I already said, we used the exactly same data set than Santos, but different methodology. And finally, after performing an atmospheric retrieval on the results using several atmospheric models, we obtained a hint of detection of water and ammonia. And we think that chocolate methodology will be especially useful either for exoplanets around young and active stars, taking into account SOAP's ability to reproduce stellar spots, and also on fast rotating stars. So thanks for your attention, and I will be happy to attend any question here or also on the Slack.
Thank you very much, Emma, for this great new technique. Questions, comments, we have plenty of time. I mean, I have many questions, but I don't want to hog all the discussion time. And if there is nobody asking question, I will ask it. So this is essentially, no, okay. So the first question was, sorry, how did you measure the radial velocity? Do you use template matching, or do you use the results that the Espresso pipeline already gives you?
Yes, we use the results from Espresso pipeline, but we also obtain, as I said, the cross correlation functions. So we did the the CCF generation with another pipeline, and we work directly with the CCFs. Okay,
yeah. I just wanted to actually, this was a point that I don't know when you did these reductions, the Espresso, I know, but you're looking at order by order, because there is a big improvement to how the Espresso pipeline calculates the CCFs that was done in the latest release of the pipeline.
Yes, we did our work in this project before that pipeline was released. So we really want to keep working in this project and to try this new Espresso pipeline to see if it improves.
I've already seen some improvement when I reduced my data, so you might want to have a go. Okay, Matteo, go ahead.
Yeah, Emma, great talk and great result. I just have a question on your final transmission spectrum. I saw there was a bin around 700 and between 700 and 750. Is that because of telluric lines that it's so noisy, or is there something with the instrument that doesn't work well?
Okay, I think it is a combination of both, but actually we think that it is more related with telluric contamination in that particular bin that wasn't well removed. That's why I plotted here this bin in a lighter thing, and also I will explain this in more detail in the paper if it finally gets accepted, that I hope it will be published soon. But yeah, I think it is mostly a problem with the tellurics, but also I have to say that there were some orders that didn't have data on this bin, and I think this is also because of the tellurics, that the CCF retrieval wasn't good enough on those orders, and that's why we don't have enough data on that bin.
The new version.
Oh, sorry, Elia, go ahead.
Sorry, I just wanted the new version of the pipeline actually in that region now just completely replaces the CCF, the data with NAND because of the problem with the tellurics. So actually it doesn't even produce CCFs anymore in those go-to orders.
Okay, yeah, definitely that's the next step.
Yeah, thanks. I'm done. Thank you.
But I think there will be further improvements to this later on once telluric correction will be integrated into the reduction pipeline. So actually, then you will get first of all telluric corrections, and then they will perform CCF. Then you will not have these problems with the orders where you have a strong telluric bands.
Okay.
It's good to see though that error propagation in this case works well. So you get a large error bar, so you wouldn't trust probably that beta bin too much, which is good. I mean, everything looks consistent to me and also consistent to the space measurement. So it's a great result, I think.
Yeah, thank you. Yeah, we are also very, we were confident about that point, that this is definitely a very different bin compared to the others in terms of the error. And also you can see that we get bigger errors on the redder part, which is also something that makes sense because of we have biggest contamination on the tellurics there.
Yeah, I think this is really fantastic because at the end, there is really, because basically what you're doing Rosetta McLaughlin without reducing the dimensionality of the analysis. So you're keeping the original CCF two-dimensional data, whereas what traditionally Chromatic Rosetta McLaughlin has done is basically just reduce it to one dimension, just RV. And that basically by doing that, you lose a lot of information. So I think your method is a great improvement on what has been done so far. And I think you can get out a lot more information than just doing traditional Chromatic Rosetta McLaughlin. It's excellent.
Yeah, thank you.
We still have 2-3 more minutes for questions for Emma. No? Okay, then I guess we can close the session. Big thank you to all the speakers for a really great start to the conference. So now we will just go for a break and reconvene at 3:40 Central European Time, where Chloe Fisher will be your session chair. Thank you, everyone.
Thank you. Bye.
Thanks.